discussed why, even though the op-amp is not an ideal op-amp, but degradations to the open loop gain does not significantly affect the closed loop gain. So just to summarize, in the ideal op-amp, the open loop gain is infinity, but in the real op-amp, the open loop gain is less than infinity, and we can expect it to be maybe 10 to the third or 10 to the fourth or 10 to the fifth. These are real op-amp open loop gain values. But previously we have figured out that this will affect not having the op-amp open loop gain being infinity. It will have an effect on the closed loop gain, G, as we have found in the formula found by here. The thing is, as we did in the practice problem, we discovered that when we change the open loop gain value, we're multiplying by 10 times 10 times 10, but the closed loop gain, it is not being severely affected. So the conclusion that we drew was that even though we changed the open loop gain drastically, the closed loop gain changes very negligibly. And so because of this, this presents the justification as to why, even though we are working with real op-amps, we can treat them as if they were ideal, and it will not deviate much from the expectation from the ideal. So let's revisit the concept of an ideal op-amp. So the next section is 2.2.3. It's called input and output resistances. So let's reintroduce the same circuit for the inverting configuration that we have been working with so far. So it's just to review, it looks like this. You put the input here, put R1 here, then you have your op-amp triangle here. You ground the non-inverting terminal. You've pulled your output and you need a feedback. So this is the inverting configuration. So just to review, let us say that R in is equal to V in divided by I in. So this is the current going in is I in, and to specify this, the voltage here is called V minus and the voltage here is called V plus. So what we can say is V in divided by, how to calculate I in, it is V in minus V minus divided by R1. But in the ideal op-amp, because the V plus is connected to ground, so then through the virtual short, then V minus is also said to be grounded. So then we can say that V in divided by V in minus 0 divided by R1 is this equals R in. So just simplify this. We say that R in is equal to the V in cancels, and this 1 over R1, so just R1. And again, we pretend this is an ideal op-amp. So we're going to be treating from now on, even though this is a real op-amp, but we're treating it as if it is an ideal op-amp, because the impact of not having infinite open loop gain is very negligible. Okay, so let's figure out now what is the output resistance. So we just repeat the same thing again, just with a little bit more circuit solving. So let's think about how to find R out. So if I put in a test signal through this V out, what would be the R out? So R out would just be V out divided by I out. So let's define I out to be whatever current I just put through the output, so I out. I'm going to call this node V minus and this one's V plus, and we know that through the virtual short both V minus and V plus is the same voltage, is 0 volts. And also when you treat the op-amp as ideal, there is no current going into the op-amp from the input terminal. So the only current that we are seeing is this current that is going through R1 and R2. We call this I1 because there's no current going in here. Okay, so you may be wondering, why do I define I1 as going from left to right? But once I finish solving, you will see that it will, when defining I1 this way, will reduce the need of having so many minus signs. With a lot of minus signs, you might lose track of the calculation. So we see that V out divided by I out is equal to R out. So let's just do some things here. R I out, as you can see, it is equal to in the reverse direction of I1. So we just do negative I1. Okay, now the same op-amp equation that we have been using all this time says that V out is equal to open loop gain times V plus minus V minus. We have been using this same equation for a very long time now, and divided by negative I1. So let's do some more circuit solving. What is I1? Well, I1 is just, we don't want to use V in because we have used that already. So let's use a different variable we have not used yet. Okay, so I will do it this way: V minus V out divided by R2. So it's just I1 is equal to this one, this voltage minus this voltage divided by this resistor. Okay, so now what to do? Well, as we have solved from before, this is treating this as if it was an ideal op-amp. So it is open loop gain multiplied by V plus is grounded, and through virtual short V minus is also 0 volts, divided by, it doesn't matter what is in this denominator because anything multiplied by 0 is 0. So it is something in this denominator, I don't want to solve it, equals 0. So R out equals 0. So now let's gonna move on to this little bit of a more advanced, just building on what we have been talking about all this time. It says, what about there's multiple resistors? So this is a related concept, but it's important to talk about it. So let's say this. Give an example problem. This actually, there's an example problem 2.2. It says that assume an op-amp to be ideal. It says find out what is closed loop gain, and if you recall, that's V out divided by V in is closed loop gain. So let's ask you find out what is this closed loop gain. I'm gonna provide the circuit to you that we're gonna solve. So we're gonna do this circuit here. Increase the size to make it more visible. Okay, so the circuit's going to be a little bit different, but the exercise is to solve something that we have not seen exactly this before. There's going to be a node here, we're going to call that Vx, and then there's going to be a resistor here, call that V3. Then there's another resistor here called R4, and then it connects here, and then V out is here. So we're going to solve this circuit now and find out what is the closed loop gain, what is G. Okay. So we're going to treat this op-amp as if it was an ideal op-amp. So in the ideal op-amp, the current going through into the op-amp is 0 amps. Okay. Voltage here and voltage here, there's a virtual short circuit. They're both 0 volts because the non-inverting terminal is grounded. Okay, so because there's no current going into the op-amp, so we call this I1, and it just goes all the way through this here. And then we're gonna call this branch here, call this I3, named after R3. And this current here is called I4, named after resistor R4. This is how we defined it. It's best practice to define it going from left to right, because you will minimize having lots of minus signs. It will be easier to keep track. Okay, so let's solve the circuit now. We say I1. Let's find out what is I1. I1 is equal to this voltage minus this voltage divided by this resistor. So it's V in minus 0 divided by R1. Another way to express this I1, you can say is this voltage minus this voltage divided by this resistor. So we can say it's equal to 0 minus Vx over R2. So simplify now. We say I1 is equal to V in divided by R1, which is also equal to negative Vx divided by R2. Now, since we are solving for what is V out divided by V in, clearly we are finding some kind of voltage relationship. Okay, so we're just going to hold on to this equation, but likely involved in the process is how can we solve for Vx, which is probably a useful value involved in this overall process. So that's the strategy that we are looking for. So let's just save this equation for now. We'll come back to that in a second. Immediately I should say, well, I'm pretty sure Vx is probably useful in this equation somehow, so let's solve for Vx. Okay, so we can say that Vx is equal to this voltage minus the voltage drop across that resistor. So it's 0 minus the voltage drop across this resistor is just I1 I1 times R2. So Vx is equal to negative I1 R2. Okay, so now we know what is Vx. So we can take this equation. There's two equations. We plug this I1 is equal to V in divided by R1. We take that and we plug it in here. So we say that Vx is equal to negative I1. So that's V in divided by R1 times R2. Now you may be wondering, how come I didn't plug this one go in here? Yeah, I could do that, but that defeats the purpose because you're plugging in Vx into an equation already having Vx. So that would not be helpful. Again, we're trying to solve for V in and V out. So it's a more logical choice to use this plug-in, right? So that's why I chose that. Okay, so let's save this equation, and I'm going to call this equation 1. We're going to save it and come back to it later. So now there is a lot of things we can do, but so we have done case VL. That's how we got to Vx. We can probably find some more equation if we do KCL this time. So this step was called KVL. Let's do KCL this time. So, and maybe KCL will generate another equation that will be useful for us. So let's try that. At this node Vx, so at node Vx, you can see there are 3 current branches. Now KCL says voltage going in puts a minus sign, and voltage coming out puts a positive sign. So I1 is going into Vx, so I1 is going into Vx, so it has a minus sign. I3 is leaving Vx, so it has a positive sign. And I4 is leaving Vx, so it has a positive sign. And all the summation of the voltage, all the summation of the currents at the same voltage node is summation to 0. So now you can say that I4 is equal to I1 minus I3. Okay. Yeah. So, okay, well, now we introduced I4. We don't know what is I4, so let's, you know, I1, we have used I1 here. I2, so on I3 we used I3. We have not used I3 yet. Okay, so let's not solve for I1. That's why we're solving for I4. We probably need to also solve for I3 later. Okay, let's do I4 first. So yeah, so what is our I4? I4 is just Vx minus this voltage divided by this resistor, right? So I4 is equal to well, actually that, yeah, let's not do that because that will keep Vx in the equation. Let's do this way actually. Let's say we don't know what is I4. But we do know what's I1. We have already solved for I1 is Vn divided by R1. And I'm trying to reuse variables in the hope that they will cancel out eventually. Okay, and what's I3? I3 is this voltage divided by this resistor. Yeah. Okay, so now let's simplify this a little bit if possible. So I4 is equal to V in divided by R1. Let's not touch that just yet. Let's worry about what is Vx. Okay, so Vx, we already solved for Vx. We solved it here in equation 1. So let's just put this as Vx. So then it is saying that negative V in Vx is equal to negative V in multiply R2 divided R1. Okay, so I4 is equal to V in over R1. A minus a negative becomes plus. V in times R2, let's just move R1 to the denominator, so it's R1, R3. You can factor out the R1, so then you say I4 is equal to you can also factor, so you can factor out this V in and you can factor out this R1. So you can do V in divided by R1 multiply 1 plus R2 over R3. And we will save this as equation 2. Save it for later. Okay. So okay, so it looks like we do have to do the V out after all. I mean V in and R1 and R2 and R2 and R3 and all of that after all. So yeah, so turns out we had to do this after all. Well, it's okay. V out, what is this voltage, is equal to this voltage minus the voltage drop across this resistor, right? So we say V out is equal to this voltage minus R4 I4. So V out is equal to Vx minus I4 R4. And you can see now why I did these things. Equation 1 goes here and equation 2 goes here. So V out is equal to equation 1 Vx negative V in divided by R1 times R2 minus I4, which is V in divided by R1 times it 1 plus R2 over R3, and then don't forget there's the R4 at the end. Yeah, okay, so so now as you can see here, this is an equation in terms of V out, V in, and resistors. Looks like Vx is gone and all the other variables that we don't like is gone. So now we can just solve for V out divided by V in, and we have solved for our gain. So this is just algebra at this point. So we say V out is equal to okay, let's not touch this first term here. We will come back to it later. let's move the R4 to the front, and then let's do distribute this Vn over R1 back. We should not have taken out, but it's too late now. So V in R2 over R1 R3. So the reason why now is it's easy, we can just factor out the V in. So we're just factoring out V in, minus R4 at 1 over R1 plus R2 over R1 R3. Okay, so now remember, gain is just V out divided by V in. So we just divide the V in to the other side. This divided by this, right? So okay, so we're just, now we have removed this V in, so we're just okay, let's just copy here so we can get rid of the extra parentheses. Okay, let's simplify by expanding all the terms. Minus R4 over R1 minus R2 R4 over R1 R2. Okay, so we have solved for gain now. We're done, but we can be done if we want to, but this is not the form, the algebraic form that the textbook is writing it in. So we just need to do some manipulation here so we can get it into a form that is the textbook uses. So yeah, that's kind of challenging, but okay, so say there's a way. What we can do is, there's an R2 here, and what we can do is we can factor out the R2, but then just introduce an R2 at the denominator here. So what I mean by that is, let's pull out this R2. So now it's just negative 1 over R1. There was no R2 here, so we have to put this R2 in this denominator. And then the last term does have R2, so we just remove it like this. That's fine. And okay, there's too many minus signs, so we get rid of minus signs. So we say remove this, factor out the minus sign, so it's just 1 over R1 plus R4 over R1 R2 plus R4 over R1 R3. Oh, and then let's do some okay, R1 is present in all three denominators, so we can also factor out the 1 over R1. So it becomes negative R2 divided by R1 multiply 1 plus R4 divide R2 plus R4 divide R3. Yes, and now we are done. This is the form that the textbook puts the problem in. So now we have did some analysis to figure out what's the gain of this circuit. This time we're having many resistors. And as you can see here, the closed loop gain only depends on the resistor values. It does not depend on the open loop gain if it's ideal op-amp. So let's we just clarify. We assume this was ideal op-amp, and when we assume it's ideal, when we assume the op-amp is ideal, then the closed loop gain only depends on the resistor values. So next, let's elaborate on this a little bit more. So next, we must find a way to design the circuit such that closed loop gain is 100. We are given some limitations. Ensure that the input resistance of 1 mega ohm, and you are prohibited from using any resistor larger than 1 mega ohm. So the question asks, we're going to modify the circuit. We're going to design a circuit such that the gain is 100, but we have some limitations. We have to ensure that the input resistance is 1 mega ohm, and we are not allowed to use any resistor in our design that is greater than 1 mega ohm. So what is this? How to do this? So as you can see, there's a lot of different requirements existing here, and we need to accommodate all of them. So this is going to be a bit of a iterative process. So we're going to do kind of like a guess a resistor value, and then we're going to check to see if the circuit works as to meet the requirements, and if it doesn't, we will modify it. And it's an iterative process. So let's just give some guess to, we're going to just guess a resistor value to choose, and then we're going to see if it works. So let's just start with R1 is equal to R2, so you just do all the 3 resistors equal to 1 mega ohm. We're not allowed to exceed 1 mega ohm, so we just started with the maximum allowed value. Maybe this will work, maybe it does not work, I don't know, we'll find out. So now according to the textbook, this works, I think. Maybe not, I don't know. So let's see what happens. So okay, we have the equation for gain. It is we're told that gain has to be 100. Oh, let's 1 mega ohm is 1 E6, right? 1 times 10 to the 6 is 1 mega ohm. So let's just do that. So that's why the gain equation is negative R2 divided by R1. So R2 is negative 1 mega ohm divided by R1 is 1 mega ohm. Just fill in. Okay, we don't know R4. R4 we calculate R4 divided by R2 is 1 mega ohm plus R4, again we don't know what it is, we're going to solve for that, and divided by 1, R3 is 1 mega ohm. So let's do this. So 100 equals you can see the mega ohm cancels, so it's just negative 1, and then multiply 1 plus you can see these are the same fractions, so it's just 2 R4 divided by 1 mega ohm. So just distribute the -1, so it's -1 minus 2R4 divided by 1 mega ohm, and then we're just solving for R4. So it's easier if we multiply everything by -1. Yeah, then we just -1 both sides, so then -101 is equal to 2R4 divided by 1 mega. Yeah, so if we use calculator, okay, actually let's do it this way. So then it becomes -101 times 1e6 is equal to R4. That becomes yeah, let's try to solve this without a calculator if possible. So it becomes -101 times E6 is equal to 2R4. So then R4 is equal to -101 E6 divided by 2. And I'm trying to not use this calculator. So it's R4 is equal to -1.0 -0.101, not a mega, and this one becomes well, okay, let's just say it's so it becomes -5.1 E6, so mega ohm. No, actually it's 50.5. But this is really big. This is too large, because the maximum resistor size is 1 mega ohm. This is 50, so this is too much. So we need to now reduce. We need to reduce R4. But now we know that R4 is going to be the biggest resistor of all. So we should know that R4 now has become our limiting resistor is R4. So if we know R4 is the largest one, we just set R4 is equal to 1 mega ohm. Like I said, this is a iterative process. And now we can just find we can find the other resistor values. So again, this iterative process involves we pick 3 resistor values, all the same, and then we solve for the 4th resistor. So if R4 is 1 mega ohm, then we're just do the same thing as before. R1 and R2 is also 1 mega ohm. That's not this. We don't change that from before. What we do change is now we're solving for R3. So the key to this iterative process is you change one resistor at a time. So now let's solve for that. Okay, gate is 100, but we are going to reuse we just skip to this point here. Okay. Actually, it's remove this minus sign, go to this negative 100. I'm going to simplify it to make things go a little bit faster. So then, so just copy this from before. Everything copied the same, because the only thing changing is we're solving for R3 this time. Plus it was R4 divided by R2, yeah, so R4 divided by R2 plus R4 divided R3. So again, all the resistors is 1 mega ohm except for R3. R3 we are just solving for that now. Okay. Oh, actually, there's no minus sign here, but okay. So now what we do is okay, so it's just negative 100 is equal to, this cancels, so it's 1 plus, this cancels, 1 plus 1e6 over R3. Okay, but the thing is, if we do this, it will give negative number. So in the interest of not having to deal with negative number, I'm just going to put another negative here, so that it becomes a positive. I don't want to deal with negative number. Again, it's not the negative positive that we're worried about, is about the size of the resistor that we are most concerned about. So I think maybe in this here there was not supposed to be a minus sign. I don't know. That's okay, whatever. This is the magnitude that is what matters the most. So okay, so minus 100 minus 1 minus 1 becomes 98. That is equal to 1e6 divided R3. So then R3 is equal to 1e6 divided like these things here. Let's just use calculator this time. So so then pointed this here. Okay, so R3 is equal to 10.2 kilo ohms, and 10.2 kilo ohms is less than 1 mega ohm. So this circuit configuration works. R1 is equal to R2 is equal to R4. They are all 1 mega ohm except for R3, which we set to 10.2 kilo ohms. So this fulfills the requirements. So let's think about what we have done here. Why did we go through all this bother to figure out these things? Okay, so let's pay attention to this R2 here. So now we have the values. R1 is 1 mega ohm, and R2 is 1 mega ohm, R3 is 10 kilo ohms, and then R4 is 1 mega ohm. So let's pay attention to what we have done just now. So R2 and R3, they are essentially in parallel, because you see we're going from this virtual short here is 0 volts going to Vx. It's basically the same as this 0 volts here on this ground going to this Vx. So these two, R2 and R3, are basically in parallel if you think about it. So let's take advantage of this approximation where we say we say that R2 and R3 is in parallel, so therefore I1 is essentially the same thing as I3. So you can see that I3 is equal to Vx minus 0 divided by R3. Let's write that down. Okay, so let's say I3 is equal to Vx minus 0 divided by R3. So let's write that. And then also R1 this time. R1 is equal to 0 minus Vx divided by R2. Oh no, R2 was just yeah. Okay, so I3 is equal to Vx over R3, and I1 is equal to negative Vx over R2. I'm going to simplify this here, solving for what is Vx is equal to negative R2 I1. Okay, and I'm solving for Vx. In this place is Vx is equal to I3 R3. So then Vx set the two equals to each other. So then we say I3 R3 is equal to negative I1 R2. Yeah, so now and just solve for I3 is equal to negative I1 times R. I could solve for I1 also, but I'm just solving for I3 because I feel like I3 is easier to solve because there is a physical direct connection to ground. But you can solve for I1. Which demonstrates the same principle. This is what I3 is. Okay. So now the textbook points out something interesting regarding I4. So let's solve for I4 and we will see what happens. So let's reuse the KCL. So negative I1 because going in, so it's negative, plus I3, positive because leaving, plus I4 is equal to 0. So let's just write that down. So it was negative I1 plus I3 plus I4 is equal to 0. So let's solve for I4. Is equal to I1 minus I3. Okay, so I4 is equal to I1. Maybe I need to plug something in for I1 later, but I don't know. But just plug in for I1 first. We just solved for I3 just now, so we can say it's negative I1 times R2 over R3. We just plug that here, and we say I4 is equal to I1 plus I1 R2 UI R3. So factor out this. I1 is equal to 1 plus R2 over R3. So the reason why the textbook wants us to do this is because it makes this observation that I4 does not depend on R4. We don't see any R4 in this equation, right? So I4 does not depend on R4. That's one observation they want us to make, which is interesting because I4 is this current here, but it doesn't even depend on this resistor. And that is one thing. The other thing that they want us to observe is we use resistors as multipliers. What they mean by that observation is like this multiply here plus this multiply here plus this multiply here. So we're just, by the principle of multiplying and dividing the resistor values, we arrive at gain. That's the observation they want us to make. In a short bit, we're going to learn about something called the weighted summer, which is like a analog. It uses this principle of adding combinations of resistor multiply and divide to analogically do addition and subtraction. It's a kind of circuit that can do that. And I'm just going to give a very brief thing. Is what if you have you want to add a bunch of signals together. So you have VN1, VN2, and then you have like VN3, 4, 5, 6, all the way to VN. So what you do is you have a R1 and R2. So this is just a principle. We'll go into depth about this more later. I just want to introduce the idea here. We have Rn here. Then we tie this to the node. And then we have a op amp here. And then we have our V out here. And then just the same feedback resistor that we've been using. Anyways, this is a circuit that can do something like this. V out is equal to negative RF multiply V in over R1 plus IVN1 plus VN2 over R2 plus, you know, so on and so forth, all the way to VNN divided by Rn. So anyways, the observation that we made is we're using the resistors as multipliers. Now later, in a later section, we will study this circuit, which takes advantage of this principle of adding together the summation for addition and subtraction of the combination of resistor multipliers. So that will come in a later example. But for now, for this circuit, this specific circuit, the other observation to realize is I4 does not depend on the value of R4, which is kind of fascinating.